In this video, we want to talk about the idea of concavity now. So this is about whether a function is what we call concave up or concave down. So in general, concave means that it has some kind of like outward curve, or like that it curves inwards, right? So that like going in from this side, it'd be curving inwards, right? So this can describe functions in general, right? Just because of what makes up the definition of a function, all of them are going to have this kind of same shape. But where they differ is where they're what we call concave up or concave down. So to kind of illustrate this, let's just take a look at the x cubed function graph first, okay? So there's a clear distinction about how this function is curving to the left of 0 and to the right of 0, right? Namely, to the right of 0, it's kind of opening upwards, and to the left of 0, it's kind of opening downwards, right? So this idea is what we call, on the left, concave down, and on the right, what we call concave up. Okay, so a more technical way of looking at it, go ahead and hand draw this graph here, is the way that the tangent lines of a function, whether they are above or below the shape of the graph. Okay, so to the right of 0 here, all of the tangent lines are going to fall below the graph, right? And to the left of 0, all of the tangent lines are going to fall above the graph. So when the tangent lines fall above the graph, this is what we call concave down. And when they fall below the graph, that's what we call concave up. Okay. So if we look back at this one, so I brought this on, this tangent slider onto this x cubed graph again, so we can see that to the right of 0, no matter where we move it, it's still, it gets kind of hard to see, but the line is still falling below the graph, right? And then if we go to the left of 0, it's always falling above the graph. Okay. So this is the idea of concavity. So this is kind of like the last piece that we need in order to make a good graph of the function. So what's going to determine concavity? What's special about 0 here? Well, if we just think about the first derivative, first of all, we know that here the first derivative is always increasing, right? And actually we can go ahead and just plop it on the graph here since we have this up. So the first derivative here, I'll move this tangent line just kind of out here so it's out of the way. The first derivative, it's always increasing because the function is always increasing because the first derivative is always positive, right? The only real point is at 0 where the derivative is 0 and also the function is constant right at that point, right at 0. But in general, we would just call this an increasing function. Okay. So, but there is something that we can see happening to the first derivative at 0, which is namely, if we look at the derivative of the first derivative, whether the first derivative is increasing or decreasing, we can see that it's decreasing until we get to 0, and then it's increasing afterwards. Okay. So this means that the function, the original function, it's increasing as we get to 0, but the amount that it's increasing by keeps decreasing, right? It's increasing by less and less as we keep going on. Till here, it's like getting pretty flat, right? It's not increasing by very much up here. So that's reflected by the graph of the derivative, which is that it's, this is telling us what the slope is, right? It just keeps getting smaller and smaller. It's decreasing until you hit 0, and then kind of the opposite thing is happening, where it's increasing by only a little bit, but then it starts increasing by more and more as you go on. Okay, so this is going to be determined by the slope of the first derivative, which is what we call the second derivative. Okay, so in general, we would say that if f double prime of x is greater than 0 for all x in some interval I, then f is concave up over I. Okay, and then if f double prime is less than 0 for all x in I, then f is concave down over I. Okay, so this of course is going to necessitate that the function be twice differentiable over the interval I, which isn't always a given, right? So we also have an equivalent for critical points to determine like where functions are changing from concave up to concave down. So I guess we could just call this a definition for inflection point. So if f is continuous at A and f changes concavity at A, then the point A, f of A is an inflection point of f. Okay. So again, the same idea, which is that we're looking for where is the second derivative positive or second derivative negative, and we the only place where it can change from negative to positive is either when it's 0 or when it's undefined. So those are going to be the same. So just like the critical points where we're looking for where is the first derivative 0 or undefined, the second derivative we're also looking for where is it 0 and where is it undefined, and then we can do a sign chart for it. Okay, so like if we just use x cubed as an example, okay, so f of x equals x cubed, f prime of x equals 3x squared, f double prime of x equals 6x. Okay, so if we want to, we would set this equal to 0, which will imply x equal to 0 is equal to 0. So x equals 0 is an inflection point. Okay, so inflection point. I guess I should say it's a possible inflection point. So this is a little bit different from the critical numbers, is that it's only called an inflection point if it actually changes from concave up to concave down, whereas it's still called a critical number even if it's the same sign on both sides, right? So it's only an inflection point if you're actually changing. So this is only a possible inflection point. So this is a sign chart for f double prime. Okay, so x is 0. So for 6x, if we put in -1, we're going to get a negative number, right? So we're doing like f double prime of -1, which should be -6. And then we're going to test f double prime of a positive number, something over here, like 1, and we get 6, right? So it changes from negative to positive, so we would say it's concave up from -infinity to 0, and concave down from 0 to infinity. Okay. And now this will allow us to make pretty good sketches of the graphs now, because we can look at the original function, we can look at where its zeros are, where is it negative or positive, we can look at its derivative, and where is that negative or positive, where is it increasing and decreasing, and now the last piece is where is it concave up, where is it concave down. So I think maybe it would be useful to, for some of our examples, let's go back through some of the ones we already looked at. Okay. So if we look at this one, for example, where we had f prime of x, so this was f of x equals 1/4 square root of x plus 1 over x, and we found that it had a local minimum at 4, right? So if you remember the shape of the graph, it actually looked like it was concave up everywhere. So that implies that when we take the second derivative of this and just analyze it, it should be something that's always positive, probably. Okay. So let's go ahead and do that and make some room here. Okay, so now when we do f double prime of x, okay, so we're just gonna basically just do the power rule with both of these, remembering that this is like x to the -1/2, right? So 1/8 times -1/2 is -1/16, and then -1/2 minus 1 will be x to the 3/2. Okay. And on the denominator still, because it's -3/2. And then this is going to be, you bring the -2 down and then subtract 1. So this is going to be a +2, because the negatives will cancel, over x cubed. Okay. So now we want to look for places where this is 0 or undefined. It is undefined at 0 still. So if we want to do a sign chart here, we'll plop 0 on there. It's our bad number. And then we want to look for where is it 0. So again, we find the common denominator. So multiply the left one by x cubed over x cubed, multiply the right one by 16, which will be end up being 32, x to the 3/2. Okay, so we get x cubed equals 0. Now, of course, again, we're only looking at the numerator, really. So this one definitely looks like it's going to be a little bit trickier. So I'm just, don't have the solutions or anything, just trying to think of like how to do this on the fly. So this part's pretty tricky. I think the best way to go about it, I'm thinking that we do a u sub, meaning we do a substitution where we let u be x cubed, which makes basically the square root of u x to the 3/2, just to get it in a little bit of a nicer form. I already did this wrong once when I cut around it, so this is attempt 2 here. So let's see, negative, so we have negative u plus root u, or 32 root u, equaling 0. So then we could do 32 root u equals u, square both sides. This is 1024 u equals u squared. Okay. So this would imply u squared minus 1024u equals 0. Factor u out. So u minus 1024 equals 0. So now u equals 0, which would imply that x equals 0. So we don't need to consider this part because that's not in the domain. Or u equals 1024. Okay. And then going back and subbing that in, that means that x cubed equals 1024, which means that x equals the cube root of 1024. 1024 is 2 to the 10th. So I'm just thinking if you want to make this any simpler, you could write this as cube root of 2 cubed times 2 to the 7th. So that's going to be 2 cube root of 2 to the 7th, which is, well, you could do more than that. Sorry. You could take out, all of that 2 to the 9th. Sorry, I don't know what I was thinking there. So cube root of 2 to the 9th would be 2 to the 3rd, which is 8. And then you're just left with the 2. Okay. So, that's definitely a little bit of a tricky one, but this substitution method, we don't use it as commonly in algebra, but this is going to be really helpful when we get to integration. So it's good to look at it now. Sorry, this was the incorrect answer that I had when I did it wrong. So now we have 8 cube root of 2 to put on here. Okay. So we could just, put in whatever we want into f prime of 2. Like 1 would be a pretty easy one to put in. Because 1's definitely less than this. So that's going to be negative 1 over 16 plus 2, which is definitely positive. Right. And then we can put in, let's see, cube root of 2 is a little over 1. So if we want to be safe, we could just put in like, I don't know, it doesn't really matter. We could put in like 9 squared, which is 81, just so it cancels out nicely with the root. So this would be, square root of 81 would be 9. So 9 cubed would be 729. So let me move over here. We have more room. So I got negative 1 over 16 times 729 plus 2 over 81 cubed. Okay, so go ahead and stick these in the calculator. So I got negative 1 over 11,664 plus 2 over 531,441. Okay. So simplified, this would be like 1 over 250,000 something. Either way, the denominator of this one, the left-hand one, is way smaller, so that one's definitely going to be larger than this one. So this is going to be less than 0. So actually not what I expected, which is that this is an inflection point, and it does go from concave up to concave down. So it's very hard to see it on the graph. I'll just go ahead and pull that back up. So we get the square root of x plus, what was it, 1 over x. Okay. So yeah, it's very hard to see. This is the minimum that we had before. So the inflection point is at 8 times the cube root of 2. So somewhere over here, like it's basically impossible to see on the graph, right? So at some point here, it does transition from concave up to concave down, which I guess does kind of make sense now with zooming out a little bit. But it's you know, it would be impossible to locate this just using the graph. So this is why it's important to have these tools to do these by hand. So I didn't expect that one to take quite so long there. You know, we can just go ahead and do an easier one real quick, a more typical problem. I like to do some of the trickier ones in the videos here, because if you can see how to do the trickier ones, then, you know, the easy ones, well, they should be easy. So if we do something like x to the fourth minus 6x cubed, okay, then f prime of x is going to be 4x cubed minus 18x squared. And then f double prime of x should be 12x squared minus 36x. So if we're looking at this one, we want to set this equal to 0. It's not going to be undefined anywhere because it's a polynomial, so we don't have to worry about that. You can go ahead and divide by 12 everywhere just to make it easier. Then we pull an x out, and we get x equals 0 or x equals 3. Okay. So we throw these on the sign chart. These are both zeros. And then we test in these intervals. Here you could use the multiplicities, so you only really need to look at one of these to see if it's negative or positive. Like, for example, if we put in 1, it's going to be 1 times negative 2, so it'll be negative, and then it's going to alternate around that. Okay, or you could just plug in numbers for all of them. So this is going to be concave up from negative infinity to 0, and 3 to infinity. Concave down from 0 to 3. Okay. So if we throw that on the graph, x to the fourth minus 6x cubed, then we can kind of see that right here. Okay, so it's concave up until 0, and then it's concave down until on the x-axis it was until 3. That goes really far down on the y-axis, but we can see where that minimum is here. And then it goes concave up the rest of the way. Okay. So you can also kind of get a picture here that the concavity does actually have an effect on the minimum or maximums. So that's called the second derivative test, which is what we'll look at in the next video.